Okay, so you have a bunch of raw data that you need to make useful. But wrangling that data can be challenging, requiring expertise, computational resources, and a lot of work to set up. To take that burden off the data scientists, businesses are now using a tool called a feature store.
In this video, we're going to look at what feature stores are, how they work, and how we can build one. So let's get started. Feature stores are a central place to build, manage, and share features across different teams in the organization. Let's try to understand how feature stores work. There is a very good video of Mike Balso, who's the co-founder of Tecton, a feature store company, where he explains how feature stores work. Let's try to see that first, and then we can dive deeper into the implementation and architecture.
How does it work? Well, let's kind of draw this out, right? So of course, the feature store, we need to serve features in production. So we have, your production application, it has to request features. The feature store has to deliver features to a model to make a prediction. It also needs to interact with your development environment. So, your notebook or your data science environment, you need to be able to talk to the feature and ask for a training data set, right? Ask for different features so you can build your models. And the feature store, of course, is connected to your upstream data, stream sources, batch sources. This can also be operational sources like operational databases, even third-party data sources, kind of common like vendor APIs. And so what's going on within the feature store? Well, there's a couple of main capabilities. First is serving. So it's all about delivering feature data to, to your model. So ML models can require a consistent view of feature data across training and serving. When we're creating training data, we need to actually train on historical examples. And so it's actually pretty common to not only need to join features together to generate a training data set, but also to have historical values of features that represent what a feature's value was at a specific point in time in the past. This is a really huge concept and one that we could do a whole deep dive on. Or from Lemonade is giving a talk on this, I think tomorrow, and on basically like all of the challenges of getting like point in time feature data. So you should check that out. And then on the serving side, your models need this feature data fresh. They need it in real time, and they need it served at scale. And so where does the feature store get this data from? Well, it has a storage layer. Feature stores contain both an online storage layer and an offline storage layer. So the online storage layer is what contains the freshest values of each feature and powers that real-time serving to your model for inference. And the offline storage layer is what contains all the historical values of different features, so such that you can go back in time for training, for assembling training data sets that represent historical examples. And the feature stores organize the data in these storage layers in a really nice way to make features really easy to join together. So they're organized by like a primary key, like an entity, we call them an entity ID, user ID for features that are user features, and they all are tagged with a timestamp so we can go through different historical values. And then feature stores actually run the feature engineering transformations to convert raw data into feature data. This happens by orchestrating transformation jobs on your existing infrastructure. So think about like running a SQL query on your warehouse or running a job on your Spark cluster. Many of these feature pipelines are expensive and they need to actually to compute a feature, you pre-compute it. You compute it ahead of time before you need it for real-time prediction. And the feature store handles two things: running those pre-computations, but also handling smart backfills for features. So when you're iterating on new features, you're doing feature engineering, as you're experimenting with new features and building new models, trying new ideas, you need historical values of features, and the feature store handles automatically backfilling those values so you can easily get a new feature set. The folks at Intuit are talking about how they manage feature transformations within their feature store. And that's a talk that's happening, I think, later today. You should check that out as well. I think that's from Simarpal and Ian. So another really important capability for this hub of data flows for your ML application is monitoring, obviously. Ensuring data quality and validating data is extremely important to anybody running a production ML application. So, the feature store is the interface between your models and your data, and they organize all the data that is important for model operation, but also for model debugging and auditing. So feature stores do not only like data quality monitoring, but they're also pluggable with external monitoring or data observability systems. So it's really about organizing these data sets, making all of the training data, the serving data accessible to any other system that wants to generate metrics and validate data quality. Feature stores can be extended not only to like monitor data quality, but also for operational metrics like serving latencies and a variety of other things around feature computation. The folks at Atlassian actually extended their feature store. They added a layer on top of Tecton that measures the cost of computation for every single feature. And so they have this whole layer of cost analytics on top of every feature. They're giving a talk on that tomorrow. You should check out Josh and Jeff's talk about that. It's really cool. The final part here is the registry. The registry is the single interface for users to interact with this, single source of truth about features in an organization. For users, it contains all of the definitions and the metadata that can be used to discover new features and share and reuse features. The registry, all the data in the registry configures the feature store system behavior. So automated jobs use the registry to figure out when to ingest data, when transformation should happen, what data to store and how to organize it. But all of this together allows the feature store to become almost this data catalog of production-ready signals. So you suddenly have this library of signals that have already been found useful for other people, and they're ready to go in production right now. What's great about this is that it removes the cold start problem for data science projects, for testing new data science ideas. Now you can essentially just like new idea, create a model with this with these set of previously existing features that others have already found useful and put it into in a full-scale production experiment in minutes. And so this dramatically speeds up the data science experimentation cycle and really solves this cold start problem. So looking at the feature store as a whole, the feature store contains a variety of components that work well together to provide a nice platform, a nice hub for all the data flows in your ML application. And it solves a lot of the data engineering challenges needed to build and maintain these production ML applications, transformations, storage, serving these features, and then monitoring them to ensure they're correct, and then the layer of discoverability and governance that's really important for sharing things across organizations.
So this is the high-level design of a feature store. There are three main components here. On the left side, there is the data sources. On the middle, there is the feature store logic, and then there is the inferencing part of it. If you look at the data sources side, you need to understand where the data is coming from, whether it is a real-time data or it is a batch data. If it is a real-time data, then it is it in Kinesis or Kafka, or if it is a batch data, whether it is using any data warehouse like Snowflake or Redshift, or it is stored in distributed file systems. And then this data basically goes into the heart of feature store. The data scientists generally do some feature transformation logic. This could be done in Spark, or it could be done in SQL, it could be done in Snowflake, dbt, or some other tools could be used. So here the actual processing happens. There are three main stages to it: the transformation side, where you're writing the logic, the storing side, and the serving side. And then on the right side, there is the inferencing layer, where you want to do the online predictions or offline predictions, or whether you want to use this for model training. There are two kinds of features, offline features and online features. Offline features are static and they don't change much, and generally they are processed in batches. You can write a SQL query or a Spark SQL against a data warehouse to get these features. Some of these features include patient age, transaction location, or an IP address. On the other hand, online features are more dynamic and they require constant processing. They generally have ultra-low latency requirements. One example that I can think of is the Z-score for real-time fraud detection. So when you calculate Z-score, you need the mean and standard deviation over a sliding window. This feature has to be calculated real time with real ultra low latency, and generally has to be accessed very fast. The best database for this could be a fast key value database to store this kind of features. Let's very briefly look at the features supported by the feature store. So one of them is feature registry. Feature registry is a place where you register your features. And the second one is data quality monitoring. This involves basically monitoring your features. It could be drift detection or other kind of things that you apply to monitor your features. Data lineage integration. So what was the transformation steps, or what were the transformations involved before generating this feature? So how do you want to track that data lineage? That's another important aspect of a feature store. Then there are two feature stores that we talked about, online and offline. The survey mechanism for both of them is different. So like if it is an offline feature store, then you need to provide some kind of an API or SDK for accessing that feature. If it is an online feature store, then you probably need a serving endpoint and a feature lookup. This has to be a near real-time computation, so the infrastructure required for this is very, very different. There would be internal tooling as well that is required, like canary testing, monitoring of these features, and audit logging. There are a lot of key components here. We can talk about them one by one. Let's start with the component called feature registry. It is one of the core component of a feature store. This is the place where you register, store, and discover your features. These could be real-time features or batch features. Generally, I wouldn't recommend building this from scratch. You can use something like an existing framework like Feast, which is an open source feature store available. It has a very good discoverability. It has a very good storing capability, so you can reuse that in your project. I wouldn't recommend going with a new central store for offline features. You can just use the existing data sources, and there is no requirement on constraints on latency, so it should be fairly straightforward to use. Some companies don't even use an offline feature store. They just consider one feature store. What you can do is, instead of using the offline feature store, you can just store the transformation logic and pre-compute the features every time. It might lead to a slower training because you need to recompute the features, but it is definitely a cost-effective solution. So let's take an example of an online feature. An online feature could be a rolling 30-minute transaction count of a credit card to predict the likelihood of a given transaction as fraudulent. A naive implementation of this could be you have a MySQL data store, which basically collects all the events from the Kafka store. So you collect all these MySQL events, and then you have the machine learning model running on the server. And every time a prediction is to be made, it makes a query to the MySQL database, computes the aggregated features, and then pass it to the model and does the prediction. So this is a very high level, very naive implementation. This can work for a small scale, but for a large scale, this will throttle, and there will be a scalability issue when it comes to addressing the latency requirements. One immediate improvement I can think of over the naive implementation is to use a NoSQL store like Redis, Cassandra, or DynamoDB. So the idea here is that the data will be coming as streams in Kafka. There will be a stream processor that processes these events. Their main responsibility is to pre-compute and aggregate these events and store the results in key value store for real-time processing by the model. So this is definitely an improvement over the existing solution, as it allows real-time computations, real-time aggregations. So there are problems with this kind of approach as well. Some of the problems I can think of is out of memory exceptions. So generally what happens is, let's say if you have to pre-compute the aggregations for a very long period of time, let's say you have to compute, if the data is coming, let's say terabytes of data per day or petabytes of data per day, and you have to compute the aggregations for last 30 days, that will be a lot of data. And generally Apache Spark or Apache Flink jobs will run out of memory because of that. Another aspect is that backfilling. Let's say if you don't have all the data available to compute aggregations for last 6 months of period, and the requirement is to do that, then there will be problems. Then you have to backfill the data. And generally what companies do is try to restrict how far back you can go. Another aspect is freshness. So how fresh is your data in the key value store? How fresh are your aggregations in the key value store? Generally, a service like Apache Spark uses sliding time window. So with sliding time window aggregations, you can choose a specific slide interval, which determines how frequently a streaming job updates these feature values. So you can set that, oh, I need aggregations per hourly basis, or it has to be done in minute basis. So that can be done using the sliding time window approach. But the problem with that is generally you cannot go below a minute level of processing. And if you need a real fresh value, then it might not be the right solution for you. Apache Flink is a better solution in this case because it allows you to do the computations right away and you don't have to wait for a minute. So that can provide you that freshness. But the problem with that is, if you have a lot of stale jobs, what that means is that not all jobs require a second level calculations, and there are some jobs that are okay with daily or hourly base, then there will be a lot of stale jobs running. So Flink can have stale jobs if that is the case. So let's look at how we're going to improve on this solution. Let's talk about the point in time feature. So what point in time means is that doing a time travel, going back to some point in history and seeing the values of these features, right? So let's say go back 1 month ago and see how these features were performing at that time. And sometimes machine learning models require that. And you cannot use a key value store for storing those historical values of these features, because it's not a real-time requirement here. It's a batch data, and it could be a lot of data. So what you generally do is to use something like a data warehouse or data lake to store this feature in the offline store, and then pass that data to the ML training framework that you have. One important aspect here is that there is a strong level of consistency required between the key value store and offline store, because initially the data comes in the key value store, and from there it is synced to the offline store for keeping the historical perspective of the data. So you continuously have to do that. So you have to make sure that right checks are in place to make sure that the data is consistent. So a minute ago we talked about how Apache Spark uses sliding time window to pre-compute these aggregations. And we also talked about the problem with that approach is basically that it cannot go below a certain frequency. So in case of Apache Spark, it was a minute. So if we need a near real-time computation, then Apache Spark might not be the solution. So how Tekton, a feature store company, how it solves that problem is using a tiled time window aggregation approach. So let's look at this approach. So at high level, the solution breaks the window aggregation over one full time window into several compacted tiles of smaller time windows, and a set of projected raw events at the head and tail of the aggregation time windows. The compacted tiles are pre-computed. So let's look at the example. So let's say if you have this pre-computed prediction service, so it makes a request to get me the aggregated data for last 4 days. So what happens is there are multiple layers here. So the first layer is the stream data, which is your Kafka, and then you have the aggregated tiles layer. So what it does is basically pre-computes that data for, like, let's say in this case 1 hour. So it will pre-compute hourly data from last 4 days and put it in the aggregated data tiles, and all the real-time data which is below 1 minute of frequency will be basically directly passed into the assembled data layer that they have. So what the goal of this assembled data is to get all these pre-computed tiles, aggregated tiles data, as well as the real-time data, and merge them together, and then return the results. So this way they solve this problem of like getting the real-time results for your aggregations. Let's try to understand a bit in more details. So in the tiled time window approach, the start period and end period of the request is not pre-computed. So let's say in this example where we need the aggregations for last 4 days. So the start period is 5th of March at 5 p.m. So we won't pre-compute that aggregation. Similarly, we won't pre-compute the start period, which is the 1st of March period. And all the things in the middle are pre-computed. So let's say 4th of March and 3rd of March and 2nd of March, those are all pre-computed. So the main idea why we don't pre-compute at the start is because we don't know what is the start time. So that aggregations that are there in the middle can only be pre-computed. So we pass this start raw events at the start, and we pass the raw events at the end to the assembled data, and that basically makes sure that everything is combined to make that final aggregations, and then it is passed to the off feature store for online surveying. So let's look at how these features are served. So in case of online surveying, basically the feature server receives a request containing the join keys to be retrieved. From these join keys, Tekton generates an online store query for all the data for the given join keys in the time range. So basically what the idea here is that the time range is always from now to some end period. So it's always start from the current time. And the idea here is that there is a function, feature definition and the request definition that the user needs to follow. So it's very template based or very configuration based approach, where you specify the data source, you specify the join keys, and and the end time also for this specific online serving, and then it will generate that aggregated data for you, and then it will pass it to the server. In case of offline serving, it is very similar, except that the data is going to the offline store or a data warehouse. The idea here is that the start time is not now, but a historical time. So you can specify the start date and end date. In this case, you will specify the join key values and a timestamp. So that's how the offline serving works. Generally, these are pre-computed using a batch Spark query that is run on the system of data warehouse, and the results are returned. Let's look at how Tecton has designed the API for the feature store. So the first step is to connect the data sources. So in case of the feature store, there are two kinds of data sources that we discuss, a batch one and the transactional one. So generally the configuration can be specified this way. So if it is a batch source, then you have to specify the batch configuration, in this case Snowflake. So you can specify the URL where the Snowflake cluster is running, what is the database, what is the schema, what is the table, and those kind of aspects. When it is a stream data source, then you have to obviously serialize and deserialize. You have to make sure that is done. And then you have to specify the stream source. In this case, there is a Kinesis configuration. You can specify what the stream name is, what is the region, position, and all those configuration parameters for connecting your stream source. After that, you need to define the features. So here you do that in the feature view. So let's say we have a feature called last transaction amount. So you specify the feature view. You say that the filter source where the data is coming from, the entities that are required, in this case user, and then the mode, whether it is Spark or something else. In this case, it will be a Spark SQL that will be run when computing this feature. What is the schedule of this? It is probably 1 day in this case, time delta. And then feature start time, when are we starting this? So this is a batch feature, so you can have configurable time. So here they have specified this as start time. So if you look at this here, so you can see that feature processing time, when was it last run, volume, and all that information is irrelevant. And then similarly, you can have another feature like a user transaction. This is called user transaction amount. So you can specify the feature view. So you can specify the filtered source. In this case, it is a stream source. And then here the start time, we specify the start time, the batch scheduler, where the data is coming from, and that aspect. And it's always computed till now. So it's always going to be run for the the start time will, and the end time will always be the current time. The start time can go back as much as we want. And these are the aggregations that needs to be applied, and this is the time window. So time delta is 5 minutes, 1 hour, 24 hours, 72 hours. And the function is mean, which is basically the average. And then similar properties. And then similarly, there is another feature which is like a binary feature. It seems like has good credit. So you can set the mode as Spark SQL. So this is a batch process, and this is the query that is used to calculate whether somebody has a good credit or not. So this is run on batches. So this, if the credit score is above this, then you conclude the batch process. So this is the second step. And then you have to materialize this feature value. So you have to compute these values, and that would be run every day. So in this case, it will be returned per second or writes per day, as you can see, and then you can write it to both online and offline store. So writes per day, and then this is the online store where you have writes per second.